Hey everybody, welcome to the video for assignment 17. This is going to cover trig graphs and power reducing identities. We're starting trig now. We've done a solid review of pre-cal. Now it's time for some trig review. And we'll start off with trig graphs and some identities. You are expected to be completely comfortable with memorized unit circle. You're, and we'll talk about that in the next video. Um, the identities, you definitely should know some identities. Pythagoreans, like sine squared plus cosine squared equals 1. Yeah, you need that, as well as rewritten versions of it, like sine squared equals 1 minus cosine squared, or secant squared um, secant squared minus 1 equals tangent squared. So please go back and review your identities. Go back and review your unit circle values. Um, hey, let's have a unit circle quiz. Um, but actually, I want to look at some identities that we didn't get to in pre-cal last year. And those are called the power-reducing identities. I put a couple in the summer packet, I believe, for you to stumble upon. We really need to take them seriously because there's a thing that we're going to do in second semester. It's going to be a thing we do every day, and when we come to that thing we do every day with a sine squared in it or a cosine squared in it, we're just going to be totally stuck. So we really need these power-reducing identities to take a problem that we can't do our calculus with and turn it into a problem that doing the calculus is easy and straightforward. Okay? So here are our power-reducing identities. We've got cosine squared equals 1 plus cosine 2x over 2. Notice it's called a power-reducing identity because we had a second degree and now we have a first degree. But look also what happened to the angle. Here we had x, and now we have 2x. So when we reduce the power, we double the angle. Okay? So, and that's because this comes actually from the double angle formulas. We also need to know sine squared x. And sine squared is very similar. It's 1 minus cosine 2x over 2. Okay? Those are our two power-reducing identities. Tangent squared, yeah, there is one, but we don't need it. And the reason we don't need it is we have this Pythagorean identity that says, oh, well, that's just secant squared minus 1. And doing that calculus thing next semester that we're going to do, it's no problem with secant squared. It is a problem with cosine squared or sine squared, but it's not a problem with secant squared. So we really only need these two power-reducing identities. I have placed an identities handout in our Office 365 folder and a blank unit circle in our Office 365 folder. So if you need those, go get those, practice with them, make sure you know these identities. What I'd like to do is a little practice with the identities. So what if I had cosine squared x times sine squared x? How could I simplify this expression? And I'd like to write the final expression where all the trig functions are to the first power, first degree. So the answer is I'm going to use my power-reducing identity. I know that cosine squared is 1 minus cosine 2x over 2. And no, it isn't, it's plus. And I know sine squared is 1 minus cosine 2x over 2. So I multiply on the bottom, and I get 4. And I FOIL on the top. Oh, look, a difference of squares, so the middle terms cancel. And I just end up with 1 minus cosine squared, right? Because cosine times cosine is cosine squared, 2x. And sure enough, we had fourth degree. Now we have second degree. I see a reduced power. That's nice. But look what happened to the angle. We had theta. Now we have 2 theta. So I'm going to take this expression and split it up because we're not done. Why aren't we done? Look, there's a squared. I need to use the power reducing identity. Okay, so when I use the power reducing identity, what happens to the angle? We notice that the angle doubles when I use the power reducing identity. So I'm going to have 1/4 minus 1/4. Now I use the power reducing identity, 1 plus cosine, don't forget to double that angle, 4x over 2. So next I'm going to split this into 2 fractions, then I'm going to distribute, and finally I'll combine like terms. So let's see what that looks like. 1/4 minus 1/4 times 1/2 minus 1/4 times 1/2 cosine 4x. So there's the splitting up. This is going to be 1/8. This is 2/8 minus 1/8 will be 1/8 minus. But when I hear I have 1/4 times 1/2, that's another 1/8 cosine 4x. There we go. First degree, had to use power reducing twice, but eventually I got there and I was able to rewrite this expression. Excellent. And you know, if I saw this next semester, I'd whimper because I can't do my calculus on that. But this, so easy. So power reducing identities will be your friend until you forget who they are, and then they will bite you in the neck and you will be very, very sad. So how about sine to the 4th? Well, I know sine to the 4th is sine squared times sine squared. Okay. Why don't, in fact, let's make it more fun. 3x, 3x, 3x. Okay, so now what can I do? Well, there's a sine squared and there's a sine squared. So I use the power reducing identity. And I'm going to have 1 minus cosine. What happens to the angle when I use the power reducing identity? It doubles over 2 times 1 minus cosine doubles 6x over 2. Okay, so I'm multiplying on the bottom, I'm foiling on top. 1 minus 2 cosine 6x. Minus times minus is plus. Cosine times cosine is cosine squared 6x all over 4. Now here I'm going to split this into 3 fractions. 1/4 minus 2/4, which is 1/2 cosine 6x. And then I still have a 1/4 cosine squared 6x. Am I done? No, because I still have this squared here. These pieces are fine, but I still have to use a power reducing identity here. So let's take this a little further. Let's use that power reducing identity a second time. 1/4 minus 1/2 cosine 6x plus 1/4, and now our power reducing identity. 1 plus cosine, what happens to the angle? Doubles, so I have 12x here over 2. I'm now going to distribute. Sure, that'll work. 1/4 minus 1/2 cosine 6x plus 1 plus cosine 12x over 8, because 4 times 2 is 8. But I really want to split this up into 2 fractions. 1/4 minus 1/2 cosine 6x plus 1/8 plus 1/8 cosine 12x. So then I've got some like terms to combine. 2/8 plus 1/8 is 3/8 minus 1/2 cosine 6x plus 1/8 cosine 12x. Ta-da! we were able to rewrite this using our power reducing identities to expressions that all are first degree. Now I think it's your turn. Will you please do this one? Cosine to the fourth 2x. So give this a try, pause the video, give this a try, and come back when you want to check your answer. Okay, welcome back. So did you think to first do cosine squared 2x times cosine squared 2x? I hope so, because now you can use your power reducing identities. 1 plus cosine, what happens to the angle? This angle doubles 4x over 2 times, this one is the same, 1 plus cosine 4x over 2. So now I have 1 plus 2 cosine 4x plus cosine squared 4x all over 4. So I did some foiling up here and combining like terms to get this expression, and on the bottom I just multiply. Okay, let's split this into 3 fractions. 2/4 is the same as 1/2 plus 1/4 cosine squared 4x. Did you stop here? Did you keep going? We need to keep going and use that power reducing identity again. 1/8 plus 1/2 cosine 4x plus 1/4. 1 plus cosine, what happens to the angle? The angle doubles over 2. So now I'm going to distribute, split this into 2 fractions, and combine like terms. So when I do that, what will I have? I'll have 1/4 plus 1/2 cosine 4x plus 1/8 plus 1/8 cosine 8x. And I see some like terms to combine. So I've got 3/8 plus 1/2 cosine 4x plus 1/8 cosine 8x. Ta-da! You did power reducing identities. Yay! So you're ready for power reducing identities. Now let's review our trig graphs. I'd like to review graphing all 6 regular trig functions and our 3 inverse trig functions. So let's start. Pi equals sine x, and we know that that graph goes from 0 to 2 pi, halfway at pi over 2, 3 pi over 2, we go up to 1 and down to -1. We start on the midline, we go up to the high point, and then back down to the low point, and we finish on the midline. There's our sine graph. But you know we're going to do more than just sine, so remind me how we do sine pi x minus pi over 2 plus 5. This is what we need to be able to graph. You'll see this on your test, maybe on a CFA. So, to review the process, 1, set the argument, i.e. the stuff in parentheses, equal to 0 and pi, 0 and 2 pi for one period, and if we were doing a second period, we would also use 4 pi. I don't believe you run into any 2 periods this year. I think we can just do 1 period and you'll be good to go. So when I do that, pi x minus pi over 2 equals 0, and pi x minus pi over 2 equals 2 pi. So I get x equals 1/2, and then this is going to be x equals 2, which is 4/2, plus 1/2 is 5/2, 5/2. Okay, so what are these? This is where the period starts, this is where the period ends. I'm going to plot those points, 1/2 and 5/2. And step 2, find quarter points. So we've got 1/2, we've got 5/2, I don't know why that looks like a 12. Halfway in between would be 3/2. Halfway in between 1/2 and 3/2, well, that's going to be 2/2, or 1. I could also find it, since the denominators are the same, remember, add the numerator, double the denominator. So 4/4, which is 1. I can add the numerator, double the denominator, and that'll be 2. Okay, so step 3, draw in sine. I guess this works for cosine as well. Okay, so sine, we know, starts on the midline, goes to its high point, back to the midline, down low, and back on the midline. So there we are. Now, we need to say this is y equals our d value. Step 4, label the sinusoidal axis with your d value. So this is y equals 5 because there's my d value. And then finally, the last step, use amplitude to label high and low y's. Okay, so our amplitude is 2. So means we're starting at 5, but we're going up 2. So this is going to be the ordered pair 1, 7. And we're starting at 5, but going down 2. So this is 2, 3. 5 minus 2 gives me 3. 5 plus 2 gives me 7. Don't forget you need to label the points on your graphs, or I give you no credit. Don't forget to show the quarter points. Okay? So since graphing sine and cosine work with the same process, and the only thing that's really different is with cosine and sine is the shape. And so remember our cosine graph, its period also goes from 0 to 2 pi, but we start high, go to the midline, down to our minimum, and then head back up again. Okay, so there's our one period of cosine. All right, so will you be so kind as to graph y equals negative 2 cosine x over 3 plus pi over 4 plus 5. Okay. Pause the video, take a few minutes to graph this, and then come back and check your answer with mine. Or if you have questions, I always think if you have questions while you're watching one of these videos, why don't you just send the question to the group meet? And I can actually maybe answer it while you're watching the video. You don't have to wait. But I would at very least write down the questions, because if you don't understand something once, you're probably not going to understand it later unless you talk about it some more. Or at the very least make some notes about it. Oh my God, I just erased the problem. Was it negative 2 cosine x over 3 plus pi over 4 plus 5? I hope so. All right. Well, welcome back. And let's graph this now. We know we need to start by setting the argument equal to 0 and equal to 2 pi. And so then we've got x over 3 equals negative pi over 4, or x equals negative pi over negative 3 pi over 4. I almost said negative pi over 12. Careful. And then over here, this is 8/4 minus 1/4, so x over 3 is 7 pi over 4. And then I multiply both sides by 3, and I get x equals 21 pi over 4. So these are the starting and ending points for one period. Negative 3 pi over 4, 21 pi over 4. I don't like drawing this y-axis in here because a lot of people turn it into one of the quarter points and then their graph is wrong. So I'm not going to do that. Instead, I'm going to find this midpoint by averaging 21 and 3. That's going to be 18 over 8, or 9 pi over 4. And let's just check that. Here the distance is 12 pi over 4, and here the distance is the same 12 pi over 4. Good. Now halfway between 9 pi over 4 and 21 pi over 4, I add the numerators. That gives me 30 pi over 4. I double the denominator, and that's 30 pi over 8, which reduces to 15 pi over 4. Okay, and I need to do that over here as well. 9 pi over 4 plus negative 3 pi over 4, 6 pi over 4 divided by 2 is 3 pi over 4. Look, no y-axis. This is not the y-axis. So we're doing negative cosine. Did you see the negative? So you start low. Make sure you start low when you see negative cosine. Drawing that shape. And the concavity is really important this year. You know, last year some people were handing in crap like this. They kind of looked like an upside down absolute value graph. No, that's not okay. Our cosine graph, our negative cosine graph, is concave up, and then it's distinctly concave down. It continues concave down, and it ends concave up. Okay? Let's label our sinusoidal axis, and then let's use the amplitude to find 9 pi over 4. Our amplitude is 2. And these points here, 21 pi over 4, I'm at 5, I go down 2, so that's a 3. I have negative 3 pi over 4, 3, as this order pairs. Okay? The amplitude is this number, not this sign. This sign tells me whether I start low and go up, or start high and go down. Okay, that's what that sign is there for. Amplitude is always a positive number. Okay? All right, well, nicely done. We've got sine and cosine done. What about secant and cosecant? Well, I remember in order to graph cosecant x, I graph the sine version first. Okay, so step 1, graph the sine version first. So if I have something like y equals 2 cosine 2x plus pi over 3 minus 7, not cosine but cosecant, I'm going to start by graphing the sine version of this. And I know that that means I'm going to set this argument equal to 0 and equal to 2 pi. And so I'm going to get x equals negative pi over 6, and this is going to be x equals 5 pi over 6. Because this is 6 pi over 3 minus 1 pi over 3 is 5 pi over 3, divided by 2 is 5 pi over 6. So I've got negative pi over 6, I have 5 pi over 6. Halfway in between, I add these, I get 4 pi over 6, 4 pi over 12. When I double the denominator, and that reduces to 2 pi over 6. I always like this one to have the same denominator as these, because now when I'm looking for this quarter point, I've got the same denominator. I can just add the tops and double the denominator. Likewise here, I can add the tops and double the denominator. We're graphing sine first for cosecant. Sine starts on the midline, goes up, comes back down to its low point, and ends on the midline. Now, our second step, where sine crosses the sinusoidal axis, draw in vertical asymptotes. So where do we cross the sinusoidal axis? Well, I see that happening here at negative pi over 6, here at 2 pi over 6, and here at 5 pi over 6. And our last step, step 3, sketch in paraboloids. So what do my paraboloids look like? Well, they look like parabolas, except they don't grow forever. They're bounded by these vertical asymptotes. So there's our positive cosecant graph. If we had a negative in front of our cosecant graph, then we would be going here and here. Okay, so what's next? Well, we need to label these points, don't we? And we know that this is pi over 12, And the amplitude, well, my amplitude is 2, and my sinusoidal axis is -7. So -7 plus 2 makes -5. And this one over here, -7 minus 2 will be -9. So there's our cosecant graph. Okay, 3 steps. For cosecant, I graph the sine version. Then, whenever this sine version crosses the sinusoidal axis, I draw in vertical asymptotes. And finally, I sketch in and label the paraboloids. How about secant? How will I do secant? Well, secant is very similar, except step 1, I draw in the cosine version first. Okay, so if I'm looking to graph y equals 1/3 secant x over 2 plus pi over 6 plus 7/3. If I want to graph this, I'm going to start by graphing the cosine version. Oh, you know what? Why don't you graph this? You can graph this. I'm sure you can. Write this down, pause the video, and graph this yourself. Remember, we draw the cosine version first. And whenever that cosine crosses the sinusoidal axis, you'll draw in vertical asymptotes. Pause the video, come back when you're done. Okay, welcome back. So I've got x over 2 plus pi over 6 equals 0, which means x equals negative pi over 3, and x over 2 plus pi over 6 equals 2 pi. That's 12 pi over 6 minus 1 pi over 6 is 11 pi over 6, but times 2. So I get x equals 22 pi over 6, or 11 pi over 3. So my graph starts at negative pi over 3 and ends at 11 pi over 3. Okay? So, now what? Well, now I need to find the quarter points. I find halfway first. 11 plus -1 is 10. So I have 10 pi over 6, 10 pi over 6, or 5 pi over 3. This distance is 6, this distance is 6 pi over 3, and I've got the right one. Now I need to go halfway between 5 pi over 3 and 11 pi over 3, halfway between 5 and 11, so that's 16 pi over 6, or 8 pi over 3. And then here, halfway between 5 and -1 is going to be 2 pi over 3. Okay, so I've got my quarter points. Negative pi over 3, 2 pi over 3, 5 pi over 3, 8 pi over 3, and 11 pi over 3. Now remember, we're doing secant, so we have to draw in the cosine version first. Cosine starts high, not on the y-axis, at the beginning of its period. Goes low, and then back up again. Okay, so there's our cosine graph. Step 2, wherever this cosine graph crosses the sinusoidal axis, we want to draw in a vertical asymptote. And then step 3, sketch in our paraboloids and label these points using our d value, y equals 7/3, and our amplitude. So 7/3 minus 1/3 is 6/3. 5 pi over 3 is 6/3, which is 2. And then up here, well, so the funny thing is, with cosecant, I get 1 up, 1 down. But with secant, I don't get 1 up, 1 down. I get a half, I get 1 down, I get a half. Or I could multiply by -1 and say I've got a half, I've got 1, I've got a half. So secant always has these half a paraboloids. So we've got this here and this here. And what are these ordered pairs? Negative pi over 3 and 7/3 plus 1/3 would be 8/3. And here we have 11 pi over 3 7/3 plus 1/3 is 8/3. And so here's our secant graph. Okay? Let me know if you have any questions about doing these trig graphs. We're going to move on to tangent and cotangent now. And remember, these are a little different. Tangent x, we set the parentheses equal to negative pi over 2 and pi over 2. Whereas for cotangent x, we set the argument equal to 0 and pi. Okay, please pay attention to these. If you don't know what to set these equal to, you probably are going to get them wrong, and then you'll have wasted all that time. It's worth taking some time to make sure that you've memorized what to set the argument equal to in each problem. Remember the characteristic shape of tangent. These are where my vertical asymptotes are. And halfway in between, we have our inflection point. Okay? Cotangent, though, looks like a negative tangent graph. It starts with 0, it ends with pi, and so this is pi over 2, 0. Remember, wherever tangent is 0, cotangent is undefined. And if tangent is undefined, cotangent will be equal to 0. Okay? Because they're reciprocals of each other. We have that reciprocal identity. So remember also, we're not using quarter points, so amplitude doesn't play a role in any of our tangent and cotangent graphs. Y equals 2 tan x over 4 plus pi over 2 plus 7. So when I think about graphing this, this plays no role. It does nothing because we're not using quarter points. I'm going to set this argument equal to negative pi over 2 and positive pi over 2. So I end up with adding pi over 2, I get 0, x equals 0, and I'm subtracting pi over 2. So that's negative pi over, x over 4 equals negative pi. X equals negative 4 pi. Okay, and then here, when I subtract pi over 2, I get 0. So this is where I have one vertical asymptote, this is where I have another. So let's sketch that in, negative 4 pi and 0. Negative 4 pi, 0. It's a positive tangent, so we draw in the positive tangent shape. We know that halfway between negative 4 pi and 0 is negative 2 pi, and the y value here is always our d. Again, this amplitude plays no role unless we were graphing quarter points. We're really not going to need to do that this year at all, which is why we didn't bother with it last year. So no quarter points. We should just know what tangent looks like and understand its shape and its vertical asymptotes. Why don't you do cotangent? Y equals cotangent pi over 2x minus pi over 3 minus 4. Okay. Do you set this equal to 0 and 2 pi? No, no, no. Remember, you set the argument for cotangent equal to, is it negative pi over 2 and pi over 2? No, no, no. It's 0 and pi. Okay. Pause the video, give this one a try, and come back and check when you're done. Okay, so pi over 2x minus pi over 3 equals 0. Pi over 2x minus pi over 3 equals 2 pi. Not 2 pi, but pi. All right, so what do we get here? We've got pi over 2x equals pi over 3. And if I multiply by the reciprocal, I get x equals 2/3. And here, 3 pi over 3 plus 1 pi over 3 is going to be 4 pi over 3. And if I multiply by the reciprocal, I end up with 8/3. So I have one vertical asymptote at 2/3. I have one vertical asymptote at 8/3. And halfway in between, I have this inflection point, 5/3, comma, whatever our d value is. Don't forget to draw in the appropriate shape. Remember, this is tangent or negative cotangent. Cotangent looks like this. Okay, that's also a negative tangent graph. All right, any questions? I wish you'd text me. That's what GroupMe is for. Last thing that we need to do is take a look at the inverse trig functions. Okay, remember our inverse trig functions are coming from our original trig functions. So when I look at sine, that's not sine, silly you. When I look at sine graph looks like this. It goes on forever in both directions. Okay? Now, when we're thinking about making an inverse, we know that the original function has to pass the horizontal line test in order for there to be an inverse. Well, this doesn't pass the horizontal line test, but we know that there's an inverse for this because we see the button on our calculator. So what we're going to have to do is we're going to have to restrict the domain so that we get all the positive sign values and all the negative sign values. And that's why our restriction goes from negative pi over 2 to pi over 2. We're only going to be having an inverse for this part of the sine graph. So think about where these points are. We've got pi over 2, 1. We've got negative pi over 2, negative 1. And we've got 0, 0. All right? So these are the points on sine within that restricted domain. Well, what points then must exist on inverse sine? Y equals sine inverse x. And we'll use synonymously arc sine x. Okay, so they're not quite, but almost completely synonyms for each other. So when you see one or the other, you can take them to mean the thing for the purposes of our class. Okay, so now we know that the points will be negative 1, negative pi over 2, 0, 0, and 1 pi over 2. Remember, on the original function, I plug in an angle and I get out an upness. With the inverse trig function, I must be plugging in an upness and getting out an angle. Okay? So what is this going to look like? Well, let's graph these points. We've got this one, negative 1, negative pi over 2. We've got this one, 0, 0. And we've got this one over here, 1 pi over 2. Now, the funny thing is you could connect those with a straight line. That's not our graph, though. Remember, as we said last year, as we head to the high point, the graph is concave up. So that's our inverse sine graph. And that's the whole inverse sine graph. It does not go beyond here. It does not go beyond here. If you put arrows on the ends here, I marked the problem wrong because there are no arrows. This is the whole graph because we had to restrict the graph of sine so that it would pass the horizontal line test. Then we flipped the x's and y's to get these x's and y's, to get these ordered pairs. So these are our reference points, 1, 2, 3. These are our reference points for arcsine. And now I'm going to do a transformation problem with arcsine. Y equals to sine inverse x over 3 plus 1 plus pi over 2. Okay. Remember, the input on inverse sine is an upness, and the output is an angle. So here's my inverse sine that I'd like to graph. We're going back to reference points. We have negative 1, negative pi over 2. We had 0, 0, and we had 1 pi over 2. Okay, I see two x transformations. I see two y transformations. I should be comfortable with this at this point. Multiplying all the y's by 2, subtracting 1 from all the x's. That gives me transition points of -2, -pi, -1, 0, and 0, pi. But I still have two more transformations to do. I need to multiply the x's by 3, and I need to add pi over 2 to the y values. And so I end up with -6, -pi over 2, -3, pi over 2, and 0, 3 pi over 2. Let's sketch that graph now. So this is -6, -pi over 2. This is -3, pi over 2. And this is 0, 3 pi over 2. Okie doke. Okie doke. Remember, we're always concave up as we head to the high point. How would this problem be different if I had a negative in front? How would this problem be different if I had a negative in front? Well, let's think about that. The x values aren't going to change at all, right? I mean, I'm still going to start with -1, -pi over 2, 0, 0, and 1 pi over 2. But I now multiply the y's by -2. I'm still going to subtract 1 from all those x's. So -2, positive pi, -1, 0, and 0, negative pi. But I have to come back and do my second set of transformations. I have to multiply the x's by 3, and I have to add pi over 2 to the y's. And so our final points, the points that we're actually going to graph, -6, 3 pi over 2, -3, pi over 2, 0, negative pi over 2. Okay, so let's take a look at this graph. So at -6, we have our biggest y value. It's up here. -6, 3 pi over 2 is here. -3, pi over 2 is here. And 0, negative pi over 2 is here. And look, that same thing I said is consistent here as well. As we head to the high point, the graph is concave up. Concave down, going to the low point, concave up, going to the high point. Okay? Now, let's take a look at inverse cosine. Inverse cosine comes from the cosine graph. Cosine graph starts high, goes low, and then back up again, but it continues forever. Doink, 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 doink. And so the question becomes, does this pass the horizontal line test? No. Where do we restrict this one's domain so that it will pass the horizontal line test? Will we use -pi over 2 and pi over 2? Well, no, from -pi over 2 to pi over 2, that doesn't pass the horizontal line test, and it only gets the positive cosine values. We need to be able to get these negative cosine values as well. So that's why this has a different restriction than inverse sine. And the restriction goes from here to here. That gets us all the positive cosine values and all the negative cosine values. So we're going from 0, 1, pi over 2, 0, and pi, -1. Okay? These are our points on cosine. So what points must exist on y equals arc cosine or cosine inverse of x? That's right, I switched the x's and y's. So I'm going to have 1, 0. I'm going to have 0 pi over 2. And I'm going to have -1 pi when I switch those x's and y's. These are my reference graphs for inverse cosine. Let's take a look at the shape. That's 1, 0, That's 0 pi over 2, and that's negative 1 pi. Okay, and again, just like inverse sine, we're going concave up to the high point. If we were doing negative inverse cosine or negative arc cosine, we'd be looking like this. Concave down, concave up. Remember, we're always concave up as we head to the high point. Always concave up as we head to the high point. All right? So perhaps you can do this transformed inverse cosine formula. Got those reference points? Okay. So how about y equals negative 4 cosine inverse x 3x plus 1 minus pi over 2. Okay, give that one a try. Come back when you're done or have questions, and we'll take a look. All right, so we've got 3x plus 1. No, we don't set the argument equal. We use transformation, silly Billy. So I've got negative 1 pi. I have 0 pi over 2. I have 1, 0. I've got two y transformations and two x transformations to do. So I multiply my y's by negative 4 because of this, and I need to subtract 1 from all the x's. My transition points will be negative 2, negative 4 pi, negative 1, negative 2 pi, and 0, 0. Okay, now what? Well, I've got a second x transformation where I divide all the x's by 3, and I have a second y transformation where I subtract pi over 2 from all the y values. So the points that I'm actually going to graph, negative 2/3, this is negative 8 minus 1 is negative 9 pi over 2, negative 1/3, negative 5 pi over 2, and 0, negative pi over 2. Those are the points I'm graphing for this negative inverse cosine graph. Remember, it's going to be my inverse cosine graph flipped upside down. This is my lowest y value. This is my highest y value. My lowest y value is negative 2/3, negative 9 pi over 2. My highest y value is at 0, negative pi over 2. And then I have that point in between negative 1/3, negative 5 pi over 2. Don't forget to draw in the appropriate shape. Remember, we're always concave up as we head to the high point. And so there's my graph. Okie doke. All right, the last thing I want to look at with you today is graphing inverse tangent. Y equals tangent inverse x. And this is really pretty easy. We don't have quarter points to worry about. Remember those vertical asymptotes at negative pi over 2 and positive pi over 2? Those are x equal things. Well, when we make the inverse, we're going to switch these x's to y's, and they're going to become horizontal asymptotes at y equals pi over 2 and y equals negative pi over 2. Remember, the output for inverse trig functions is an angle. The input would be the tangent value. And what's the shape look like? The shape looks like kind of like a logistic curve. And this point would be 0, 0. Now, remember I've been saying a lot recently that when I go to the high place, I'm concave up. Well, that's true for inverse sine and inverse cosine, but not true for inverse tangent. Okay? If I were concave up, I'd be crossing that horizontal asymptote. And yeah, no. I'll never cross these horizontal asymptotes. Some horizontal asymptotes can be crossed, but not these. So that's my reference graph. Okay, it's just got these two y values here and this xy ordered pair here. So if I see some sort of y equals 2 tangent inverse x minus 1 plus pi over 4, okay? I'm going to say, well, I don't have a lot to work with. I've got 0, 0. I've got y equals negative pi over 2 and y equals positive pi over 2. and I'm going to carry out my transformations. I see that I need to multiply all the y's by 2, because these are y's, I multiply them by 2. And I need to add 1 to the x's. Oops, no x's over there. That's the only x value. So my transition points will be 1, 0, y equals negative pi, y equals pi. But I still need to add pi over 4 to all the y values, plus pi over 4, plus pi over 4, plus pi over 4. And so I end up with 1 pi over 4 as my inflection point. This asymptote is at negative 3 pi over 4, and this asymptote is at 5 pi over 4. So what does our graph look like? Well, let's take a look. We have two horizontal asymptotes, one at y equals negative 3 pi over 4, one at y equals 5 pi over 4. We draw in our inverse tangent shape, label that inflection point, and that inflection point is 1 comma pi over 4. Okie doke. Well, that's it for today. I hope this was a useful review on how to do all 9 trig and inverse trig graphs, as well as talking about power-reducing identities. We've got 2 more days of trig review before we dig into reviewing for this chapter test, but we're coming to an end of pre-cal trig, and when we get to chapter 2, we're going to start calculus, and you're going to say, calculus? This is calculus? This is so easy. All right. Have a great day, everyone. Remember, your homework tonight is assignment 17. It's a worksheet in our Office 365 folder. So look for it there, and let me know if you have any difficulty finding it, or send questions to the GroupMe about doing it. All right, take care, everyone.